Hi everyone. In the lecture 9, an analytic expression for the inversion charge is introduced. This figure shows a numerical simulation result for MOS structure. Its oxide thickness is 2 nanometer and the substrate doping density is 10 to the 18 per cubic centimeter. As we can see, when the gate voltage increases, the absolute value of a negative charge in the substrate increases. However, it is not a straight line. It can be decomposed into two terms. One is related with the depletion charge. Its absolute value is shown as a blue curve. Another term is related with the inversion electrons. Up to about 0.5 volt, this term is negligible. Beyond that voltage, it becomes a dominant term. Assume that the gate voltage is higher than the threshold voltage. One important observation is the electrostatic potential at the interface. The surface potential is almost fixed. We can find a similar situation in the PN junction. Since the diode current is exponentially dependent on the diode voltage beyond VD on, the diode voltage cannot exceed VD on. Quite similarly, since the electron density is exponentially dependent on the surface potential for gate voltages above the threshold voltage, the surface potential cannot exceed the value at the threshold. Usually, we are interested with the integrated electron density. The integrated charge due to the inversion electrons is defined as follows. Of course, it has a negative value. Let me show you simple analytic expressions for Qelec. When the gate voltage is higher than the threshold voltage, the electrostatic potential in the p-type substrate is almost fixed. An additional gate voltage is applied only to the oxide layer. Therefore, it behaves like a capacitor for the additional voltage. Note that there is an offset, the threshold voltage. When the gate voltage is lower than VTH, almost no electron charge is found. The analytic expressions, black dashed line, are drawn over the numerical result, green solid line. As we can see, both lines agree quite well. In each region, below VTH or above VTH, the Qelec versus VG curve is linear. However, the entire Qelec versus VG curve is not linear. The main advantage of this QV curve is found at the zero gate voltage. When Vg equal to 0, we have no electron. Even under a noisy environment, we can switch off our transistor. Only when we apply a significantly high voltage, we can have electrons. The digital circuit uses either 0 volt or VDD. The analog circuit may use various gate voltages. In general, with a large Cox, we can collect many electrons under a given gate area. Therefore, a large Cox is preferred and a thin oxide layer is desirable. In the case of VTH, an appropriate value depends on VDD. Since VDD has been reduced from 5 volt to 0.7 volt during several decades, the threshold voltage also has been reduced. These parameters are critically important. However, they are determined by the manufacturer. Under a given technology, designers can select the circuit topology and sizes of transistors. In the next video, a transistor based on the MOS structure will be introduced. Thank you.